Hi, the lesson that we're going to be discussing in this video is decision tables. And we'll start with some of the application areas where decision tables can be very useful. I'll walk through the steps for creating a decision table based on verbiage that you have been given that's describing a problem. And we'll look at an exercise, maybe even several exercises to demonstrate the process. A decision table takes the form of a chart, and it lists at the top part of the chart things called causes or inputs. And then at the bottom portion, we see results or effects. Each column along the table represents some unique combination of the causes. And the purpose or use of a decision table is to be robust in structuring the logic in a complex problem statement. The great reason to understand decision tables is they apply to so many areas. They apply to the business field, so all the applications that have to do with retail and logistics and point of sale can be often described in the form of a decision table. Programmers will be very familiar with decision tables because these are a great tool for really structuring your thinking when working out a more than intuitive kind of problem. Those that work in the fields of testing will use decision tables to map out all the various ways that a machine or software may operate so that they make sure that they cover all the possibilities when they're designing test cases. Hardware design, city planning, many areas where decision tables apply. So let us discuss all of the steps that you need to take to create a proper decision table. First, you need to understand and list out all the causes or input conditions in your problem. Secondly, you're going to need to calculate the number of possible combinations that you will have when interleaving all of those causes. Then we're going to fill out the columns with all the possible combinations, and there is a methodical way to do this. Often we want to reduce those combinations so the logic becomes less onerous. And then you always want to verify or do a check on your decision table to make sure that you didn't make any errors and you have the correct formulation. And then, of course, you want to see the outcomes or effects in the table. So the first step is to list all the inputs or causes. and you're going to want to write down the values in some, easily recognizable, easily interpretable name for these causes. And it's a good idea to keep those things together that are closely related, and that will become more clear as we actually do an example problem. Along with that concept, it's a good idea to put what's called the most dominating cause first. And again, an example will help to clarify what that means. But by putting something that is the most prominent at the top of the cause, it just will make the rest of the chart a little more simple to create. And when there are causes that have lots of possible values, we want those to be furthest down the list. And again, once we get through the actual method of filling out the chart, it will also become clear why that's a good idea. So if all of your causes or inputs are simply yes, no values, that really makes the whole decision table pretty straightforward. And you'll soon find out that the total number of cases that you're going to have, or the total number of columns, is 2 raised to the number of causes. So let's take a look at what that means. If you have 3 different causes down your table, and each of those are yes, no values, then you're going to have 2 to the third or 8 columns necessary. So how do we fill out these columns? Well, the first thing that it's recommended that you do is determine this entity called the repeating factor, or RF. And the repeating factor is obtained by multiplying the number of possible values for each of your causes on the rows that are below the row in question. Now, that's a lot of words. Let's try to look over here and see what we mean. So if we were looking at row 1, the repeating factor would be determined by covering up row 1, either imaginarily or for real, and then looking below it. So we have 2 possibilities, yes, no, and then 2 more possibilities of yes, no. So 2 times 2 is 4. So the repeating factor for row 1 is 4, meaning we put y, followed by n, 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 n. So we repeat y 4 times and then repeat n 4 times. Moving down to the second row, if we imaginarily or for real cover up the second row and above, then only 2 values appear below. And 2 is the repeating factor. So we have YY and N, YY and N. And then always on your last row, the repeating factor is 1, which means you just alternate through the values or cycle through the values. If there's just 2 values, yes and no, then you're alternating YN, 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 YN. Okay. And you can see that we needed 8 columns, which were the number of values 2 raised to the number of causes, 2 to the 3rd power, which is 8. We'll talk about the effects very soon. So once we determine that repeating factor and fill out all the combinations, we're really close to being ready to, analyze our problem and break down what are called the effects. So to simplify things, we may want to reduce some combinations. Those are what we call the don't care conditions. And those would be the areas where 2 columns would produce identical results. It wouldn't matter then whether there would be one value or another value in a particular cause. You were still going to get the same effect or result. And that is the case here with columns 3 and 4. We have either a Y or an N. It really doesn't matter because the 2 effects were the same. So we can do a thing called collapsing the column so that columns 3 and 4 become one single column with Y for cause 1, N for cause 2, and like a don't care for cause 3, leading to effect 1. So we're joining columns where the values are identical and including items that are don't care conditions. Now, the cautionary note is make sure absolutely positively that the effects are the same when you're collapsing the columns, because if they're not, then they weren't really the same, were they? So there is a possibility to calculate something called a checksum. So it's a double check. And how you do this is for each column, you calculate the number of combinations it represents. So in the case of a column that has all of its values filled out, it represents 1 combination. If you have a column like column 1 with a don't care in its position, then that column actually represents both of these values. So that represents 2 conditions. And in the case of column 4 actually represents 4 conditions because it's 2 and 2. So the checksum is calculated based on those representations, and we add them up 2 plus 1 plus 1 plus 4 equals 8. Well, what is 8? 8 was the number of original columns that we started with. So if we can add up that checksum data and obtain the number of original columns, that should give us some assurance that we did not make any gaffes or errors along the way. And of course, the last step we need to do is to add the outcomes to the table. So we want to go back to the English verbiage that we were supplied with that talked about the causes and effects and map those into the chart. And it is possible that a particular effect could occur in more than one combination across. So now's the time to give it a try. Here is an example of a problem specification. A mailing is sent out to customers, and the content of the mailing is about discounting for potential new offers. And the content happens to be different for different types of customers. So we're just going to have like fictional customers. So we got customer types A and customer types B. And they're going to get a basic letter. But customer type C is going to get a special letter. And just to add complexity, any customers with 2 or more credit lines concurrently or credit ratings with this special category X, they're going to get some special paragraph in their letter with an offer to subscribe to more discounting. So you can see where this problem from retail or business has rules as part of the verbiage. But the rules can start to get a little like unwieldy and complex and, hard to unwind. And to just hand this to a programmer or some other developer, it can be easily misinterpreted. So this is where we want to use the tool of a decision table to help us think it out. So you can think about the problem. You can try to work it out using the previously discussed steps. You can pause the video here if you want to do that. But I'll just move on and talk about the solution. So in this case, we had customer types, and we had 3 customer types, A, B, and C. And because the customer type had the most values associated with it, I put it up toward the top of the decision table. If a customer had 2 or more lines of credit, that's another cause, another input. And that answer to that question was either yes or no. So that is the next cause. And then there was that special magic credit rating of X. And again, the customer either had that or didn't. So it was a yes or a no. If we took that customer type row and imaginarily covered it up and looked below it, we had 2 values and 2 values. That created 2 times 2, or a repeating factor of 4. Okay, so the repeating factor is 4. So A, B, C, C. Moving down to the next row, we virtually cover that up and see the repeating factor is 2. 2 N's, 2 Y's, 2 N's, and the last row always just cycles through. Now we can go back to the verbiage that we were supplied with to map out the effects. So if it was a customer type A and that customer had 2 or more lines of credit and a special credit rating of X, they were going to get the normal letter, which was more or less the template, and an additional paragraph to their letter. And that was the same case for that customer A, really whether they had 2 or more lines of credit or not. You can move back to the verbiage to unwind or interpret the causes and effects. So there's a lot to think about in the systems analysis stage of the software development lifecycle. And we can continue our thought with another example. Here is one called City Bus Lines, and they are developing an information system that will monitor passenger traffic, peak travel hours, and equipment requirements. So the IT manager wants you to document a process called balance that determines whether extra buses should be assigned to a particular route. The balance process will automatically assign buses to a given route, but only if the route is behind schedule and all the other routes are on schedule. But a supervisor can always override the automatic balance to assign extra resources. So the first admonition is to create a decision table that describes the city bus lines balance process. And then, of course, you could move on to simplify. Often it's a good idea to use a decision table template to make your work a little more neat and easy. So here is one that is pre-made for you, and you can find on Moodle the template file. So what we want to do is write out the causes and work out the combinations. So one of the causes is the supervisor override, which is mentioned near the end of the paragraph. And we can either have one of those or not. And our other causes are that this route on time, and then all other routes on time. And in each of these conditions, or in each of these cases, it is a yes or a no option. Because we have 3 causes, each with 2 options, we should be able to see that we will need 8 columns to start our process. If we cover up the first row virtually, we can see 2 times 2 gives us a repeating factor of 4. So I will repeat the y 4 times, followed by the n 4 times. In the second row, the repeating factor is 2. So 2 y's, 2 n's, 2 y's, and 2 n's. And of course, in the bottom, we will alternate back and forth between yes and no for our values. What are the effects? In this problem, there's really just one outcome, which is we're adding additional buses. We're just deciding whether we're going to do that or not. And in fact, if there is a supervisor override, we are going to add those buses, no argument. If there's not a supervisor override and this route was on time, there was no need to add additional buses. If the current route was not on time, but all other routes are on time, we are told that we should add additional buses, or that our balance algorithm, our balance routine, should add additional buses. If this route is on time, no need to. And as well, if our route is not on time, but all the other routes are also not running on time, no, we're not supposed to add any additional buses. So this is the first draft, let's say, of our decision table worked out for us. And then we can consider whether some of the columns can be combined or collapsed based on common outcomes. And if we see that if we analyze those columns and look at what's called the don't care conditions, that we can collapse some columns. In the case of the supervisor override, we do collapsing and have don't cares whether this bus route is on time or any of the other routes are on time. We collapse all 4 of those columns into a single column where the outcome of adding an additional bus is yes in all those cases. When there was no supervisor override, but this bus route was on time, then it didn't matter about the other routes. We did not add additional buses. And then the final two columns were remaining intact. Now we have a much simpler representation of the decisions. And decision tables are great, but there's also another graphical tool called a decision tree. And I can take this table and reimagine it as the decision tree that describes the city bus lines balance process. So we see a supervisor override starting point where adding additional buses always occurs, and then the non-supervisor override condition where we have it forking out into two possibilities. This route's on time or it's not on time. And then in the case of the route being on time, we don't add buses. If it's not on time, we have to ask another question and decide no additional buses or add additional buses. And you can see, I think you can see that the decision tree is something that is pretty easy for a programmer to wrap their mind around and really takes that original specification and lays it out very clearly. So graphical tools, including decision tables and decision trees, are important additionals to the systems analyst toolkit.